Hey, good evening, Amit.
Yeah, hi, good evening. So, hello everyone. So, I think my audio, video, and sharing everything is working fine. Okay, so let's wait for 4 to 5 minutes and after that we will start.
So,
Hello. Okay, so we have waited enough. So, let's start. So, once again, good evening everyone. I welcome you all to the live session number 7 for the week 7 for the NPTEL course Hydrogen Energy Production, Storage, Transportation and Safety. The course instructor is Professor Pratibha Sharma from IIT Bombay, and I am this course TA Amit Kumar Sharma. And this meeting is being recorded. So the meeting recording and this PPT will be shared to you from the NPTEL team. So those who are not able to attend today, they can see the videos and use the PPT later. So this is the course outline. So as of now, in previous 6 weeks, we have covered the hydrogen production, global status, hydrogen storage. Okay. So currently we are discussing about hydrogen storage. So question number one is which one out of the following compressors is a non-mechanical compressor? Reciprocating compressor, diaphragm compressor, liquid compressor, metal hydride based compressor. So the question is asking which one is the non-mechanical compressor. So you have given four options. Let me know the right answer.
It's a metal hydride based compressor.
Okay, so we have one answer, metal hydride based compressor. So what do you mean by non-mechanical compressor?
Means there is no any rotational movement or mechanical movement is there.
Okay, yeah, nice. So basically there is no means of mechanical components, mechanical, you can say some kind of energy that is given from mechanical components is used to do the compression. Anybody else? So what about the reciprocating compressor? So as the name suggests, reciprocating. So it means that, and we know if you have gone through the classes, so there will be a piston cylinder and then there will be compression and expansion. Similar in diaphragm also, there will be kind of mechanical energy involved in liquid compressor also. But in metal hydride based compressor, there is no mechanical component. And in later slides, we will go through this metal hydride based compressor to learn more about this. So the correct answer is D. So here you can see the classification of hydrogen compressors. So basically, we have two types of major categories. One is mechanical, second one is non-mechanical compressor. So in mechanical compressor, you have positive displacement type and dynamic. In positive displacement type, you have reciprocating, diaphragm, linear, and liquid compressor. So these four comes under the positive displacement type category under the mechanical compressor. On the other side, we have also dynamic and centrifugal category in mechanical compressors. In non-mechanical, we have cryo compression, adsorption based compressor, metal hydride, and electrochemical compressor. So these compressor are non-mechanical. So there will be no mechanical kind of equipment or energy will be involved to do the compression. So now see the options. So only this metal hydride is matching with this category. Okay. So for non-mechanical, we have four: cryocompression, adsorption, metal hydride, and electrochemical compression. Now let's go through these compressors one by one. So this one is the cryogenic compression. So normally we compress hydrogen in a gas form to a particular pressure to a higher pressure. Okay. But in cryogenic compression, we are compressing the liquid hydrogen. Okay. So because the main issue with storage is the density. So we want to have more hydrogen in a less space. Okay. So we want to have higher density of hydrogen. That our that is our main objective. So a good thing is to do to store the liquid hydrogen because we know that density of liquid hydrogen will be higher. So here we are having a cryogenic pump that can pump the liquid hydrogen and store it. So the twice the volumetric efficiency of a mechanical compressor. The technology challenges continuous monitoring of thermal insulation and the performance like geometry and material of vessel used. So this is the cryogenic compression. For more detail, you can refer to this article. So let's here see, you can see at room temperature. So 4.1 kg of hydrogen at 75 MPa and volume is 100 liter. At 77 Kelvin, you can say it's 15 MPa. Okay, with the weight is the same. Okay, so you can see if we use the liquid hydrogen, we can have twice the volumetric efficiency. We can store more hydrogen. So the reduction in liner thickness. So what are the benefits? So reduction in liner thickness. The lighter density alloys as shell, we need to use lighter density alloys for shell. The best thing is to 9.2 weight% of aluminum alloy is used. So it is used for automotive applications using 50 MPa cryo compressed tank. So you can have 91% improvement in gravimetric capacity. So advantage high volumetric efficiency, high energy density, and high gravimetric and volumetric capacities. So what are disadvantages? Because we need to use liquid hydrogen, so you need to have a very low temperature. So requirement of low temperature, and you are handling this liquid hydrogen, then your thermal insulation is a critical thing. So you need to monitor it very comprehensively. And liquefaction cost and the vacuum stability. So currently Linde is a company, so they are having this kind of compression. The output pressure they have 35 to 90 MPa. Flow rate is greater than 1000 normal meter cube per hour. Now let's see about the metal hydride compressors. Yeah, Chandrasekhar.
Yeah, in the previous slide, it is mentioned as cryo condition in automotive application.
Mm-hmm.
Um, at least when I went through the lecture sessions there, I was trying to first search and who is exactly using a cryo compressed vessel. Is it something, is it in development or is it in commercial? At least I
No,
could not
no, no,
find.
no. It's under development. Yeah,
Okay. Yeah, okay. Yeah, fine then.
yeah.
Then fine.
It's
Yeah,
under
okay.
development. Yeah,
Yeah, okay.
because there are still so many limitations. So, but
Too many.
the thing is, yeah. So the thing is that if you are having this kind of system, this kind of arrangement in automotive application, then you don't have to worry about the refilling.
Hmm.
That is one
That's
thing.
correct. That's correct.
Yeah,
Yeah. Okay.
yeah. And also you can consider this also like directly it is not used in the automotives, but it can be used for the hydrogen refilling station. So if you are having a
Yes.
hydrogen vehicle, so you are
Yeah.
having this kind of vessels.
Yeah.
So yeah, so
That's correct.
this you can confirm like Linde. So they are having this kind of
Yes.
vessel, so they can use for hydrogen refilling station. So it's also a kind of automotive application, not directly in the automotive, but
Yeah.
for automotive applications.
Correct. This is on board. It can't be used on board, but
Yeah,
on ground, on a fixed stationary station, it can be.
fixed
Yes, that's correct.
stations. Yeah,
Yeah,
yeah.
that's correct.
So metal hydride compressors. So as the name suggests, metal hydride. So here we will use a kind of metal, and there will be some kind of reaction so that hydrogen can be stored. So it is a thermal sorption type compressor. You can see there is a metal, then the hydrogen is there. They will react and form metal hydride and heat will be released. Okay. So this is the forward reaction. In the backward, if you supply the heat to metal hydride, then this metal hydride will release the hydrogen and again become the metal. So the purpose of this is it is this kind of compression is volumetrically efficient. It is safe because suppose if there is any leakage, then what will happen? Because if you want to have the hydrogen from the metal hydride, you need to supply some kind of energy. So if there is a leakage, so that the supplied energy will also diluted. So after some time, the leak will be arrested. So the no further backward reaction will be there, and there will be no hydrogen. So it is a considered as a safe operation. So the most important component of metal hydride depends on the characteristics of metal hydrides. So the characteristics of metal hydride is very important. So further we will learn more about this metal hydrides in our solid state storage of hydrogen lecture. So there are some requirements of metal hydrides. So it should have tunable pressure composition temperature required to achieve the compression ratio in the temperature range of lower to higher, high reversible capacity, fast kinetics, low plateau slope, low hysteresis, cyclic stability, tolerance toward impurities, scalability, and low cost. So if you see in a process, like in a process diagram, so it's a TS diagram. The hydrogen compression is an ideal compression cycle, can have these four process: isobaric from 1 to 2, then polytropic heating, then isobaric isothermal desorption, then polytropic cooling. Okay, so these can be divided into these four process. For more details, please refer to the class notes. So in a single stage compressor, the single cycle, if you have multi-stage, then there will be a, so this is the desorption. So this will be further connected to another cycle. Okay. So in that the stage 1, then stage 2. So you can have multi-stage compression. So there will be successive absorption and desorption in several beds. So low pressure hydrides desorbs at TH, which matches with the absorption into the high pressure metal hydride at TL. You can connect it here. So this TH, this will be TL. So they will match and it will be connected. So the requirements for this is to select appropriate material, design the various component methods and accessories for supplying and removal of heat. So these are the major requirements for these kind of compressors. So normally the metal hydride storage bed is kind of cylindrical. So there is a central space, central artery. Then there is annular space. So in this there will be hydrogen. So space with metal hydride, then heat exchange mechanism. Desorption produce increase in pressure to desired pressure. The compression by sequence of cooling and heating of metal hydride control by heat transfer, because we know we need to have the involvement of heat for the forward and backward reaction. So multi-stage compression with series of coupled modules containing metal hydride with different pressure at same temperature, allowing progressive increase in pressure. So is there any questions, Chandrasekhar? I can see your hand is raised. Okay.
No, no, sorry, I forgot loading my hand.
Yeah. Okay. So if we are using the metal hydride compressors, then the efficiency will be low due to losses in the heat transfer, heat requirement for desorption, and energy for cooling requirement. So due to these, the efficiency will be low. So currently, HISA system South Africa, they have developed a metal hydride based compressor for hydrogen refueling stations. So advantage, thermally driven device, no moving parts, compact and simple. So non-mechanical, no moving parts. Disadvantage, appropriate choice of alloys, low efficiency and requirement of thermal management. These are the disadvantages. So in summary, we can say with no non-mechanical compressors are more compact because there are no moving parts. They are simple and compact. We can have noise-free operation and safe and reliable. Question number 2. Which compressor has the lowest specific energy requirement? Lowest specific energy requirement. Diaphragm compressor, ionic liquid compressor, piston compressor, and metal hydride based compressor. Try to remember. So I advise you all, please go through the class videos before this live session so that you can have a basic idea, so that will help you to solve the questions.
Sir, B, ionic liquid compression.
Okay, we have an answer B. And what is your reasoning?
Reasonings are just studied, I think. I mean,
Sorry.
it was there in the lecture. That's it.
Okay,
Reasoning and
so it's good you have gone through the lectures. So we have answer B, ionic liquid compressors. Yes, it's correct. So let's see, learn about it. So in ionic liquid compressors, so we use low melting point salts. So at room temperature in a molten state, they have good thermal and chemical stability, high ionic conductivity, moderate viscosity, high polarity, negligible volatility, environmental friendly and fire retardants. So also they have very good lubricating properties and low compressibility for high pressure applications. So currently Linde is having 90 to 340 normal meter cube per hour of ionic liquid compressors that can give you the 90 MPa in 5 steps, and it is used for hydrogen refueling stations. And you can have high volumetric efficiency and high compression ratio. And good lubricant and coolant properties give you high efficiency. So the advantage of ionic liquid compressors is the no contamination because there is no lubricating oil. It's better than reciprocating compressors, and low energy consumption, long service life, low material cost, low noise, high compression ratio, nearly isothermal operations, and very few moving parts involved. But still, it has some disadvantages like corrosion is high, decreases efficiency, and contamination by corrosion products, increased maintenance cost due to this corrosion and all. Liquid can leave compression chamber, so liquid traps is required. Cavitation can be also there. So anybody know about cavitation?
yes, sir. And that output pressure gone down below vapor pressure. Then there is a sound, the vapor blast. So that phenomena. I just telling briefly that phenomena called the cavitation.
Yeah, nice. So normally we have multiple times seen the cavitation phenomena in the fluid dynamics when you are dealing with the pumps, turbines and all, but in the compression also. So in this the gas will trapped in the liquid, and then you can have there will be bubbles, and when they will blast, so that can cause the cavitation, and that can hamper the inner, that can damage the inner structure, like the inner, like what is the, you can say the inner material that are having in the compressors, so that can damage the equipments. So the liquid compressors, so positive displacement device, it is suitable for hydrogen. Here we use liquid to compress gas, no sliding seal. We can achieve almost isothermal condition because we are using liquid, so it will be a very, there will be good thermal management. So we can achieve a almost isothermal condition, efficient and cost effective compression. Liquid gas compressed, density difference, no need of external cooling, cost saving. It have much higher efficiency than other mechanical compressors. So now let's see. So this is the block diagram. So we can see inlet. There is a pump. It is pumping the liquid. So here you can see the piston. So it's moving upward. So here the gas will be compressed and will leave out at high pressure. And similarly, this is coming down. So it is again inlet gas is coming. Again, when the liquid will be pushed, so it will go upward and gas will be compressed, and you can have high pressure outlet. So compression by a moving piston, by liquid columns move back and forth driven by a pump. So the pump is the pushing the liquid. Used for compressed air, 20-30 megapascal porous media can be used to improve heat transfer, reduce leak, improve efficiency, eliminate dead volume. Internal liquid spray cooling used to improve heat transfer. So this is a very good review paper. You can search and read more about these compressors. Now liquid rotary compressor. So it is used to compress gas with high liquid content in a stator frame and impeller with a series of blades extending radially. Impeller forces liquid to move, forming ring and compressing gases. Not used widely to lower efficiency. So we can also have a liquid rotary compressor where we use the centrifugal force for the compression. So in summary, so the ionic compressors have very high efficiency, up to 70%. They can compress to a high pressure from 0.5 ampere to 100 ampere in 5 steps. Energy required 2.7 kilowatt hour per kg. Liquid compressors, low vapor pressure, low solubility of hydrogen, good tribological properties. Then centrifugal compressor can also be used, but low molecular weight of hydrogen, high tip speed required, purity problems from seals, contamination, vibration, rotor dynamics, lower efficiency, impellers failure. So these are the challenges with this. So the major challenges with mechanical compressors: contamination, complexity, reliability, maintenance. Okay, consume 5 to 15% of energy content in compression, large size to loads, larger footprint required, and larger power requirement. These are the major challenges with the mechanical compressors. The high cost, it accounts 54% for capex, 28% for energy consumption, and 18% for OPEX in hydrogen refueling stations. What is the major limitation of using lubricating oil in reciprocating compressor? A. Hydrogen leak proof. B. Increases wear and tear. C. Contamination. D. Increases friction losses.
It's contamination.
Contamination.
Okay. So we have one answer, contamination. Okay, so it's correct. So because if you are having lubricating oil, then there is chances of contamination from that oil. Because if you are using the lubricating oil, then it will not increase the wear and tear. It will decrease. It will not increase the friction. It will decrease. Okay. So now let's have a comparison of various hydrogen compressors. So the piston compressor, the flow rate up to 10,000 normal meter cube per hour, efficiency up to 45%, cost 1,70,000 USD, energy consumption less than 5 kilowatt hour per kg. So advantages: mature technology, adaptable to high flow rate, because we can see it can go up to 10,000 normal meter cube per hour. High discharge pressure, contamination by lubricating oil. So it is actually not advantage, it should be a disadvantage. It should come here. So disadvantage: moving parts, complexity, heat transfer management is difficult, not good for high pressure, and vibration and noise embrittlement. Now diaphragm compressor, flow rate less than 1,000 meter cube per hour, efficiency 45%, 2,300 USD per kg per day. Then energy consumption less than 5. Advantage: low power requirement, low cooling, fit for handling pure gas. Disadvantages: diaphragm failure, complex design, restricted throughput. Then ionic liquid compressors less than 1,000, efficiency greater than 70. The energy consumption only 2.7. We have already covered equation, the lowest energy consumption. So that is for ionic liquid compressors. It is in the range of 2.7. High efficiency, high compression ratio, low energy consumption, reduced wear and friction, long life, low noise, quiet operation, nearly isothermal, less number of moving parts, no gas contamination. But there is an issue of liquid can enter gas chamber, cavitation of gas in liquid, and the corrosion. For metal hydride based compressors, flow rate less than 10, efficiency less than 10, very low efficiency, energy consumption very high. So in the previous three compressors, for the ionic liquid, it was only 2.7, for other two less than 5, but for this it is around 10. Advantages: thermally driven, so waste heat can be used, because we need to have heat for the reaction to happen. Absence of moving part, no noise, compact and simple, high purity hydrogen, and it is considered as a safe. Disadvantages: appropriate choice of material, good thermal management, low efficiency, high weight, and low compression ratio. Electrochemical compressors, very low flow rate, less than 10 meter cube per hour only. Efficiency 60%, almost 170 USD per kg per day. Advantage: low cost, no moving parts, high purity hydrogen, high compression efficiency, low cost operation. But we also have some difficulties in manufacturing, in sealing, high cell resistance, low compression ratio, low discharge pressure, and the adsorption based, we don't have so much data for this. The advantages are no sealing, no moving part, no vibration and noise, and low cost material. Disadvantages: low thermal conductivity, problem in thermal management, low temperature operation, and high OPEX. So in these compressor, we can see clearly that this ionic liquid is having lowest energy consumption. So in summary, we can see the capex and opex are higher for mechanical compressors, and efficiency are lower. Ionic liquid compressors have high efficiency, can compress 100 MPa in 5 steps, low specific energy consumption, 2.7 kilowatt hour per gas as against mechanical. So metal hydride compressors capex and opex both are lower than the conventional mechanical compressors. Metal hydride compressors require less power to drive compression. Significant advantage of weight and volume in metal hydride compression. Specific energy consumption of metal hydride compressors high due to poor thermal conductivity of metal hydride and high heat of absorption. The capex of electrochemical compressors low per unit of hydrogen compression rate versus mechanical compression. So for the EHC, the OPEX is 1 USD per kg versus 1.75 to 2.3 USD per kg for reciprocating. So the OPEX is also lower for electrochemical compressors. The specific energy consumption for electrochemical compression is also low, depends on compression ratio, and also efficiency depends on the compression ratio. Adsorption based compressors is an emerging field, so we can expect low capex but high opex. So it's still under development. Question number 4. Linear compressors are based upon which thermodynamic cycle? Stirling, Rankine, vapor compression, refrigeration cycle, or diesel cycle, Otto cycle?
Is it Rankine cycle?
Anybody else? So linear compressors are based upon Stirling cycle. Rankine cycle is widely used in the power plant. So Stirling cycle is used in the linear compressor. So let's see more about it. So it is a diagram of a linear compressor. You can see a piston, inlet wall, outlet wall, a cylinder. This piston is connected with springs, and then we have a arrangement here. Then we have motor, then the magnet. So, so these springs are controlled through this motor. So here it is for cryogenic applications, less number of moving parts. There is no rod crank assembly, absence of rotating parts, simple and cost effective. Linear motors. So here you can see moving coil, moving magnet type. So moving coil, so we can have high efficiency, long life, lower noise and vibration. So series of hollow coils in a strong magnetic field, or we can also use large permanent magnets. So magnet is moving, so we can have good heat dissipating, high reliability. So moving magnet, this in middle provide movement and high magnetic flux with small magnets. So we can invert the polarity. So in that way it will move up or down, so that we can have compression and expansion. Magnetic motors operate at resonant frequency. So piston cylinder separated by a gas bearing system. Gas act as a pad to reduce friction. No lubricating oil. So no contamination, low noise, silent operation. Okay, we have covered this. Control system design is complicated. Okay. So we are having advantages. It is compact, high reliable, high efficiency, low noise and vibration, long operation of life, and reduce number of moving part. Disadvantage, control of piston displacement and operated resonant conditions. So we have reported efficiency of greater than 73% with flow 1112 millimeter cube per hour. Input pressure 2 megapascal, output 8695 megapascal. So which compressor is suitable for high flow rate? Diaphragm, centrifugal, reciprocating, metal hydride.
It's a reciprocating compressor. We have already covered, I think.
And what is the maximum flow rate that we can go in the
Maybe
range of
10,000.
yes.
10,000.
So in previous slides we have covered this. There's reciprocating compressor can go up to 10,000 normal meter cube per hour of flow rate. Okay. The correct answer is C. Reciprocating compressor. So here you can see we are having a cylinder, then the inlet wall, delivery wall, piston, we have a connecting rod and crank. So when the piston is coming downwards, so the pressure will come down here and there will be suction of hydrogen. When the piston is going up, then this wall will be closed. This wall is closed. So the whole hydrogen will be compressed. And when the piston reaches up to top dead center, then this wall will open and you can have the compressed hydrogen. Okay. So we can have compression ratio up to maximum achievable temperature. So for the compression ratio, there will be limitation of maximum achievable temperature because as we compress any gas, the temperature will increase. So we are having limitation of temperature. Okay. Flow rate is limited by cylinder dimension and speed of compression. So if you want to have larger flow, then the cylinder volume will increase. So basically the cost will increase. Okay. Hydrogen embrittlement, the selection of material and design is very critical. Otherwise, there can be hydrogen embrittlement. So you need to have special alloy, special steel, alloy steel, cast iron, cast or forged steel, liner coating on cylinder walls. So if you have liner coating, then you can reduce the cost of maintenance and also diameter can be changed. If you want to change diameter, then you can increase the coating thickness. So we can also have a two-stage compression. So here you can see the first stage and second stage. So they are connected with a moving cylinder. So when there is a compression in this stage, there will be suction here. Then this gas will go here. Then it will be further compressed. So we can have final compression in two stages. So here your low pressure gas will go into the first stage. Then after a particular compression, it will go into the second stage and there will be further compression and you can have high pressure gas outlet. So as you can see, we are having the moving piston in a cylinder. So there will be wear and friction will be there due to this mechanical involvement. To reduce that, we have to use a lubrication. Okay, so we can use lubricating oils to improve reliability, reduce wear, minimize leakage, and to have good life. But if you are using oil, then there will be chances of contamination. So to prevent contact between the piston and cylinder in non-lubricating thermoplastic material used, rider bands and piston rings prevent leakages. So to prevent the leakages, we can use the piston rings, and to prevent the contact between piston and cylinder, non-lubricating thermoplastic metals can be used. wear and leakage is more in non-lubricating ones and less life, so less contamination by abrasive particles. So if you are using for high pressure and oil free, then early failure of sealing rings because of non-uniformity of pressure distribution. Two compartment distance piece is used for gas venting and avoid embrittlement. So with the reciprocating compressor, we can have wide range of capacity, flow rate and delivery pressure. By proper selection of material and design, we can reduce the speed of compression, discharge pressure of 100 megapascal and flow rates of 1000 of normal meter cube per hour. So this kind of compressors are ideal for moderate flow rates and high pressure. So you can see the hydropack. So input 35 megapascal, output 85.9 megapascal. Flow rate 4820 normal meter cube per hour for the hydrogen refueling station and for gas storage vessels. So also there are some reports of 10,000 normal meter cube per hour and output of 25 megapascal. Then Hitachi is working with input 0.6, output 100 megapascal. And flow rate 300 normal meter cube per hour for HRS and gas storage vessels. You can see the change in pressure and the flow rate is very high. So still we have challenges because it's kind of mechanical. Then the moving parts are there, the cost of maintenance, complexity, the cooling is difficult due to moving parts and heat produced. The pressure fluctuation detrimental, causing vibration and noise, reduce system life. So it is most widely used, mature technology, have good performance. You can have high discharge pressure, flexibility in size and capacity. Moving parts, disadvantage, moving parts, contamination, maintenance and difficulty in thermal management, embrittlement and vibration and noise. So for to have a good compression, we need to have better materials for ring and seals, better materials for piston and so we need to have less wear and friction and we need to have continuous monitoring for early detection of failure. Using lighter density alloy like aluminum as a liner material to fabricate cryo compressed tank can improve system gravimetric capacity too.
I think it is 9.2, the D.
Yes, so direct question. So the gravimetric capacity can improve by the 9.2 weight percent. What is the gravimetric capacity? Anybody? Anybody? Think about it. So gravimetric capacity, like refer the mass of hydrogen to the mass of
Cylinder or
yeah mass of the cylinder. You can say the metal they used for the storage. So basically in that particular material we can store that much of hydrogen. So I think I'm right. So but please check it. Okay. But it's related to the mass. Okay. So if we are using the aluminum as a alloy, so we can increase the gravimetric capacity. Basically, we can store more hydrogen in, or we require lower weight of the storage vessel. Which phenomena is termed as a back diffusion? Permeation of hydrogen ion from the cathode to anode, permeation of hydrogen ion from anode to cathode, permeation of H2 molecule from cathode to anode, or hydrogen molecule from anode to cathode.
Sir, A, formation of H plus
From cathode to anode, that is A.
Okay, we have one answer A. Just wait for 1 minute. Anybody else? Correct answer is A. So the back diffusion is when there is a permeation of hydrogen ion from cathode to anode, and it is connected to which compression? So if you know the answer A, so you should also know the compression.
Electro compression, some electro EHC.
Yeah, electrochemical compression.
Yeah.
So let's see. So this is electrochemical compression. Here the principle is quite similar to the PEM fuel cell, polymer exchange membrane fuel cell. So it is used for smaller quantities of hydrogen to be compressed to have high pressure. The principle is similar to PEM fuel cell. Low pressure hydrogen on the anode side of the compressor, and it undergoes the following reaction. At anode, you can see the hydrogen will convert into hydrogen ions and two electrons. On the cathode, the electrons will pass through the membrane to the cathode side. The electrons come through the external circuit and they will combine at the cathode. So there's a difference that in the PEM fuel cell, your cathode is open, but here it is closed. There is no supply on the cathode side. Okay, so that this hydrogen will be collected at cathode, and if this reaction is continuously going on, then what will happen at the cathode side? There will be buildup of pressure, and after reaching a particular pressure, you can have your required gas at that particular pressure. So difference from the PEM fuel cell is that no gas supplied to the cathode side. The driving force is electrical energy supplied, and getting high pressure has both practical and economic challenge. So you have anode, cathode, then the gas diffusion layer, GDL, then membrane, electrical supply. Okay. So advantages. So isothermal compression of hydrogen is efficient, low energy demand, high discharge pressure, can be used for purifying hydrogen, no moving parts, robust and require very less maintenance, low cost, both compression purification, high hydrogen purity, and high efficiency. Anybody want to tell me why the purity is very high? Why the purity of hydrogen is very high in electrochemical compression? Just see this and think about it. Take your time. It's important to understand this. How we can comment on purity?
Yeah, because there is no other mechanical component no, which can reduce the purity. Here it is simple the molecular reaction.
So mechanical component are not there, then you can say, okay, there will be less noise, there will be efficiency can be good, but how can you comment on purity? The question is that how are you sure that purity will be very high? Because we are specifically saying this. Now, see the diagram very carefully. Yeah.
See,
No other gas is there.
Where?
So the bullet point says the difference is no gas supplied at anode cathode side.
So this bullet point is representing that what is the difference between the PEM fuel cell and this compression. So in PEM fuel cell, everything is similar. Only thing that we are having the supply of oxygen on the cathode side, but there is no gases on the supplied on the cathode side in this.
will there be any difference in the membrane, polymer membrane here?
No, membrane also same. So in PEM fuel cell also we need to have a membrane that can supply the H plus ion.
Correct.
Sir, at the cathode side, the pressure does not immediately change to high pressure. It first
No.
continuously.
Just okay. That is only regarding the pressure. Just focus on the what is the basic principle. How this compression is happening. What is the basic principle? Just look at that point. Then you will get to know, okay, why the purity is very high. What is the basic fundamental? How this compression is happening?
So because of this reversible reaction. Because
Okay. So what is unique in that reaction?
because whatever hydrogen and electron is generated, they are again going back to the same state, that is producing the hydrogen.
So yeah, so the main thing is that let's look at this reaction actually and this membrane. So this membrane is specifically designed to pass only hydrogen ions. So when you are passing the hydrogen ions, so the gas molecule is the whole gas molecule is not going. Okay, only the hydrogen ions are going, and here they are combining again. So suppose your low pressure gas may can have some kind of impurities, but this membrane will pass only H plus ion. Okay, so this is the beauty of the system. So because only the hydrogen ions can permeate this membrane. So on this side, there will be pure hydrogen only. So we can comment because we are using a membrane that can specifically pass the hydrogen ions only. No other gas or any impurity can pass through this membrane. That's why you can comment on, okay, your purity will be very high. Suppose this low pressure gas was having 97% purity, but here you can have 99.999% purity. If you are not having any like leakage from top side and all, that is the other case. But if everything is fine, then purity can be 99.999%. Okay, but this system is also have some disadvantages. Efficiency decreases with pressure, increasing pressure. Back diffusion of hydrogen increases with pressure difference. So some hydrogen, because this side the pressure is lower, this side pressure is higher, so some hydrogen molecule can transfer back. Getting high pressure has both practical and economic challenge, and requirement of sealing is there. So there is a current project, Pedrus. So you are having P out 100 MPa, flow rate 0.93 meter cube per hour. Another project having P out 40 MPa, flow 28 normal meter cube per hour. Which problems occur in compressed hydrogen tank when hydrogen gas gets trapped between liner and composite? Buckling, blistering, plastic deformation, fatigue.
It's a blistering.
Okay, we have one answer, blistering. So yes, it's correct. So the blistering can happen when hydrogen gas gets trapped between the liner and the composite. So now let's learn more about the compressed hydrogen tanks.
Sir, what is blistering?
So blistering, you can say there will be some so the exact I need to check actually. Anybody?
Yeah, blistering is a phenomenon when these molecules get below the primary layer and then it starts expanding. It's a bubble formation will start happening, and that over a period of time that will spurt out. That will open up. When you imagine a cavitation, if you imagine in a blistering if you imagine cavitation, the gas bubbles which come, those gas bubbles will get entrapped on the below the surface, and as the pressure increase, they burst. When they burst, they open up the surface also, and they'll start going in and in. Or you can imagine if you have any fire if you have any thermal thing on your hand or anywhere in your skin, you'll start getting blisters.
Yeah.
It is, you can imagine that.
So
Imagine like
basically
that.
it can like this. So if you are having your
So,
yeah,
so it
so
is
you have
bulging of that
little bit, yeah, little
surface.
bit. So it
No, no,
can weaken the your tank material, and in the long go the tank can fail. Okay. Anybody else? So basically hydrogen atoms diffuse into a metal, accumulate in voids and combine to form hydrogen gas. This buildup of hydrogen gas increases pressure beneath the metal surface, causing blisters to form. So basically then blister will form and it can weaken the material. It's not good for the storage tank. So because at that point the stress will be higher and the chances of failure will increase. Okay. So now learn about compressed hydrogen tanks. So the hydrogen
Sorry,
tanks
sir.
can vary. Yeah.
One question: how to avoid this blistering? Then
So blistering we will go through. Maybe we can improve the liner so the gas will not trapped between the liner and the composite. And also the selection of material, because the gas will absorb into the trapped in between, then only it will happen. So you need to do something. So I'm also not sure about this. Maybe we will go through and let's see if anything is mentioned in upcoming slides or not. So application we can use for industrial, commercial, automotives and space. So the capacity, so it can be in small bottle and large storage tanks, vessels. So to have the bottles and pressure vessels, because we know we need to store hydrogen very high pressure. So for the usage and maintenance, for the manufacturing, we need to have a proper guidance. So these are governed by the various standards and have clearly stated guidelines. Requirements are different for stationary and vehicular application. The volumetric density, storage density is 23 kg per meter cube for 35 megapascal and 38 kg per meter cube for 70 megapascal. Important data. So requirement, safety, strength, durability, because we need to have safety, because if we are using tanks in the for vehicular application, then there can be any accident. Okay, so it should have proper safety, strength and durability. So we need to use special materials also. So we have four type of compressed hydrogen tanks: type 1, 2, 3 and 4. So type 1 is made up of all metal. You can store up to 200 to 300 bar, high strength but high weight. So strength is more because it is made up of all metal. Weight is also high. For industrial and commercial use. Type 2 made up of thick metal liner providing gas tightness. Then hoop wrapped with fiber resin composite prevents metal liner fatigue and stresses. Fiber also provides strength. Resin binding of fibers provide load transfer, prevents against environment and wear. In type 3, made up of thin metallic liner and fully wrapped with fiber. And resin composite strength and stiffness can be more than previous types. Weight reduced to half of type 1, but cost twice of type 2. So as you are moving downwards, the weight is reducing, but the cost is increasing. Type 4, made up of polymer liners, gas tightness, and fully wrapped with fiber resin composite, mechanical strength, and bear the load. Usually have cylindrical section, two domes, polar opening for filling and emptying. The consideration are weight and volume, safety, cost, application, and end use requirement. These are the major consideration for these tanks. Now let's see the types. So cylindrical, then two is mentioned here, two domes. Okay, so this type 1 all metal, type 2 the liner is metal, but you have composite fiber resin outside. In type 3 you liner metal and composite fiber resin. In type 4 liner polymer, okay, and there is also a metal for the gas outlet. So there can be some leakage because it's changing, so you need to prevent that. Plus composite fiber plus resin. So this is another diagram. You can see it's fully open, it's partially wrapped, and it's wrapped. Then it's also have fully wrapped with polymer and this composite resin and liner polymer. So what are the design consideration for a hydrogen storage tank? So we have a service pressure and test pressure. Anybody, do you know what is the service pressure and test pressure?
Service pressure means working pressure, and test pressure is we need to test it at around 1.5 times of the working pressure.
Yes, nice. So because we are considering the factor of safety. So the test pressure is 1.5 times higher than the service pressure. So it will be your operating pressure, okay, or the maximum pressure that you can have in your system. The test pressure, the cylinder will be tested at that particular pressure. Okay, so this cylinder, this bottle can store up to this pressure without failure. You need to also consider the external stresses when you use, because there will be impacts, vibration, temperature, weight of the accessories, and the aggressive media. Cycle life, safety, failure modes, fatigue, buckling, creeping, plastic deformation for metals, for composite, cracks, delamination, aging, fiber rupture, blistering or linear collapse, hydrogen trapped between liner and composite, mechanical strength, hydrogen embrittlement, compatibility with gases. So these are the design considerations you need to consider. The choice of material and design are of prime importance, because choice of material and design, they are only responsible for these. Okay. Metals are isotropic while composites, the mechanical properties are concentrated in the fiber direction, failure modes and aging is different. So if you are using the metal bottle or fiber bottle, then the modes and aging will be different in both cases. So which process is used to fabricate liners from polymers and monomers? Extrusion, milling, roto molding process, and forging.
Rotomolding process.
We have one answer, roto molding. Okay, so this is correct. So in the metallic vessels, we need to consider the stresses. So domes are normally oversized in type 1. thick liner and only hoop wrapped in type 2. It can withstand high pressure. For composite wrapping lab design, we can use using finite element for optimized design. For the metallic type 1, from plates, billets or tubes, and also type 2 and type 3 liners. Polymer liners can be made using roto molding process from polymers or monomers. So this is about this question. Introduction mold, then heating and cooling along with rotating metallic boss either introduced during roto molding or fixed or liner before wrapping. This metallic boss is important because the joining should be perfect, otherwise there will be leakage. From polymer tubes by extrusion, blow molding, the composite either hoop or fully wrapping using a fiber winding machine. After wrapping, resins and cured using either by heat treatment or by UV exposure. So these are the system followed for the cylinder designs. The materials, like for metallic, we have AL6061, these are the codes, or 7060, steel, inox or polymer, polyethylene or polyamide based polymers, composite, glass, aramid or carbon fiber embedded in resin. For resin, polyester, epoxy or phenolic. Epoxy can have good mechanical properties, stability and compatibility with the fiber winding. So what are the major challenges in compressed hydrogen tanks? So we can have challenge to have high pressure, hydrogen embrittlement, gas permeation in polymers type 4, polymer liner and the Bose junction, because temperature variation is there, liner deformation during emptying and filling. High cost, because as we are increasing the type, the cost is increasing and the weight is reducing. The quick emptying of the vessel, deformation of liner, and cylinder lifetime. So to have proper functioning, the periodic assessment is important. So to have this assessment, we should have a non-destructive technique for monitoring required. What is this non-destructive technique? Anybody? What is the meaning of non-destructive testing?
Means
Yes,
no
like
damage to the
ultrasound.
tank.
Yeah, no physical damage.
Yeah, there should be no physical alteration testing directly on the material, so that can damage the cylinder. So basically non-destructive. What is the volumetric energy density that could be achieved for hydrogen compressed at 35 megapascal in compressed hydrogen tank?
23 kg per meter cube.
23.
So have you calculated it or you remember?
No, just before one slide was there, na important
Okay,
data.
nice. So just consider this as a numerical. Now just consider ideal gas behavior. Ideal gas behavior. And now calculate the density at this pressure. Consider isothermal compression. Now let me know the density. Density at NTP is how much?
0.089.
0.89.
Okay. So I have given you some data. Now calculate the density considering ideal gas behavior.
Sir, what is to be, I mean, what is the question here?
The question is that because the initial question we have given the volumetric energy density that could be achieved for hydrogen compressed at 35 megapascal. So suppose you are having the hydrogen at NTP and you are compressing it to 35 megapascal. Then you need to calculate the density because you know the density will change. So the question is given, but question have not mentioned about the behavior of gas, the compression. So, but you know the answer is 23. Okay. But now I have given you conditions that you need to consider the ideal gas behavior. You need to consider the isothermal compression. Now calculate the density at final pressure of 35 megapascal. If the density at NTP is 0.089 kg per meter cube. This is the question. So what will be the density at 35 megapascal? This is the question, and these are the condition. Ideal gas, compression is isothermal. Just try to follow ideal gas equation. I think you will have the answer. Any answer?
So 1.41 kg per meter cube.
1 point?
41.
No. It's very low, no? 1.41. Consider the units carefully. It's megapascal.
31.15 kg.
Yes, yes. 31 point. So how did you calculate this?
Okay, sir, I consider that the PB equal to MRT. So in that case, M is constant. I mean, not M is constant. It is P equal to M by V because T is constant, the isothermal process. So M by V is the density. So, so if we consider P1 equal to M1 by V1, so at P1 equal to 0.089, and what will be at 350 bar. So 35 megapascal equal to 350 bar, approximately 350 at atmospheric pressure. So 0.89 into 350 is coming this 31.
Yes. So this is the ideal gas. PV equals to MRT. Just transfer the volume this side so it can become the density. So P1 equals to rho 1 RT1 for state 1. For state 2, P2 equals to rho 2 RT2. Okay. I have given the condition isothermal. So T1, T2 will be same. If I divide both equations, so it will become P1 upon P2 equals to rho 1 upon rho 2. This R cancel out, T1, T2 cancel out. So we need to calculate density P2. So rho 2. So rho 2 will be rho 1
Into P2.
into P2 upon P1. Okay. So P1 you consider 1 atmosphere. So it can consider the 35 megapascal. So 350 bar. And rho 1 you have 0.089. So rho 2 will be 0.089 multiplied by 351. So it will give you how much?
31.15.
Yes, 31.15 kg per meter cube. But what is the answer? The answer is 23 kg per meter cube. Why?
Compressibility. It's not ideal gas.
Yes, nice. So as we cannot consider it as ideal gas, so we need to consider the compressibility factor. Okay, so because we have in our previous class, we have also seen that using the ideal gas behavior, we may overestimate the density. Okay, overestimate the values. So we need to use the real gas equations. Van der Waals equation you can use some, there are some different models are also there for the real gas behavior. So you need to use those models to calculate the density. So when you apply those models, the answer will be 23. Okay, let's move further. Which one out of the following is a
It's the diaphragm
typical
compressor.
diaphragm? Okay. So just a moment, I'm having some issue on my side in the Teams. Okay. Everything is fine?
Yes,
Can
yes,
you
fine.
see
Yes.
me? Can you hear me?
Yeah.
Okay, okay. So the answer you were saying option D.
Option D, diaphragm compressor.
Okay, so your answer is correct. The question is positive displacement type. So we have seen in our second slide about the categories of compressors. So diaphragm one is come under the positive displacement compressor. Okay. Now let's learn more about this. So here we have a piston driven reciprocating machine, but don't have any moving part in gas compression chamber. So the chamber is not having any moving part, but still we have a piston driven reciprocating machine. So it can have high throughput, less cooling requirement, less power requirement, and effective. Fit for handling pure gases because we are not having moving parts. We are not using the oil for the lubrication. So it can fit for handling pure gases. Gas is isolated from the piston. Diaphragm isolates gas chamber from hydraulic chamber. Diaphragm made up of 3 plates. Hydraulic fluid so that oil governs the diaphragm movement. So we are having a hydraulic fluid which is governing the movement of diaphragm. Now this is the diagram. So here you can see the piston. It is connected with a crank drive. This is cylinder and here is a space. So this space is a oil space. Here oil will be filled and here you can see the diaphragm. So this is the final position when diaphragm at the top end after the compression, and this is the initial position when the suction is going on. Okay, so this is the movement of diaphragm you can see from this to this. So these are the ports, inlet, outlet. This is the gas space. Okay, so when there will be suction, so piston will come down. So this diaphragm will come this side. Okay, at this position. So what will happen? This valve will open, inlet valve will open, the hydrogen gas come inside this chamber. Once the chamber will be once this chamber is full, then the piston is going upward. So it will push this oil. This oil will push this diaphragm and it will start moving in the left direction. So at the end it is like this. So this gas will totally compressed and you open this valve and you can have the compressed hydrogen. Okay, so this is the basic working. So the hydraulic circuit provides oil in the oil space. Hydraulic pressure limiter controls pressure. The perforated plates act as a oil distributor. Oil pressure control required to improve efficiency and life. There is no direct contact of piston with the gas. Okay, this oil is only pushing the diaphragm from left to right. Okay, so this is the diaphragm compressor. So as there is no direct contact of gas with the oil, because in the reciprocating one, this is the cylinder and piston is moving up and down and we need to have oil here. So some part of oil can be on these walls and that can come in contact with the gas and can contaminate that. But here the oil is directly outside the diaphragm and the compression happening in this chamber, and this chamber is not having any kind of oil. Okay, this gas space is not having any kind of oil. So here the hydraulic and the gas circuit separated, so no contamination. This is the major advantage of the system. Better cooling than other reciprocating compressors. Cooling in cover high surface area of diaphragm and chamber. Cooled oil you can use. The operate close to isothermal conditions. So the work input will be lower. High compression ratio, reduced number of stages. Diaphragm separates oils and hydrogen. Design and material important. Highly durable and corrosion resistant. So for for the diaphragm plates, you can use stainless steel, chrome nickel, stainless steel, copper, barium alloys, duplex steel. Hydrogen leakage is minimum, and it's important for the hydrogen refueling stations. We also have electrostatic diaphragm compressor. So in this, instead of the oil and piston, we are having a DC voltage source. So we are changing the polarity for the movement of this diaphragm from left to right. So we can eliminate the complex system that was having the oil, the piston and all. So we can have a simplest system. So, but it's good for small capacities. Okay. The thing is that we have changed the setting. We are controlling the diaphragm through the DC voltage. So there are some challenges for the diaphragm compressors like durability, diaphragm failure, mechanical stresses, the diaphragm design advantage, high efficiency. They are compact, high throughput, lower power consumption, less cooling requirement, fit for handling pure gases. Also, they are fit for handling pure gases because there is no contact of the piston or any material with the gas. The chambers are totally different. Disadvantages: failure of diaphragm, complexity, flow rate limitation. So for a good compressor, we need to have a well designed and durable diaphragm. These are the companies, they have these kind of compressors with inlet pressure of 0.5 to 3.5 megapascal, output 428 megapascal, flow rate 5 to 581 meter cube per hour. So in summary, these are most widely used, technologically mature, reciprocating compressor used when high flow rates required, like thousands of nanometer cube per hour. So, but hydrogen can leak from the seals. Hydrogen can combine with metals to undergo hydrogen embrittlement. Structural complexity, high maintenance cost, reciprocating due to moving parts, lubricating ones can be used, but contamination of hydrogen can be there. Diaphragm suitable for low flow rates. Which of the process is the compression stroke in a reciprocating compressor? Movement of piston from TDC to BDC with delivery valve open. Movement of piston from BDC to TDC with delivery valve closed. Movement of piston from TDC to BDC with delivery valve closed. Then movement of piston from BDC to TDC with delivery valve open.
It is 2B.
Option B. What is the BDC and TDC?
Bottom dead center and top dead center. When the
What are
piston is towards crank end, it is BDC. When it towards the top, that is towards the valve, it is TDC.
okay?
That's where the valves open and you get compressed.
Yeah, nice. So, which of the process is the compression stroke? So, if I make a simple suppose this is inlet, outlet, and we are having a piston. Okay. So the question is compression. So for the compression, piston should go up or down.
Piston, both I and O are closed, and piston will be moving up.
Yes. So both should be closed and piston should be moving up. Okay. So suppose this is the PDC, this is the TDC, top dead center, bottom dead center. So piston will not go through the bottom dead center and piston will not go upward from the top dead center. So these are the limits. So TDC and BDC are the limit of the piston movement. TDC is the highest point up to where the piston can go. The BDC is the lowest point up to where the piston can go. Okay. So for the compression, the delivery valve should be closed. Okay. And it should go from BDC to TDC. So when it is moving, so what is happening? The volume is reducing. Volume is reducing, but so and there is no inlet and outlet. So the gas that is present in this volume will now present in this volume. So what will happen? The pressure will increase. So for the compression stroke, the movement of piston from BDC to TDC with the delivery valve closed. Movement of piston is accomplished by which type of motor in linear compressor? Linear motor, induction motor, BLDC, synchronous.
Linear motor.
Induction.
It is linear motor.
Okay, we have answer linear motor. Anybody else?
The induction motor.
Okay. No, it is we are using the linear motor in the linear compressor because the movement is we only specifically need the linear movement of the piston. So we need to have a linear motor.
Okay.
Liquid compressors are space type of compressors: positive displacement, rotor displacement, electrochemical, non-mechanical.
Non-mechanical.
Positive displacement.
So let's go back to the slide number first. So if you see this slide, so in this you can see the type of compressor: mechanical, non-mechanical. Mechanical have the positive displacement and dynamic. So in the positive displacement, reciprocating, diaphragm, linear and liquid compressor. Dynamic comes centrifugal. Okay. So basically what is the meaning of positive displacement? So what is the basic similarity in these reciprocating, diaphragm, linear and liquid compressor? What are the similarities in these four? So what is happening in the reciprocating? You are having a piston, okay, and you are moving that piston to compress the gas. What is happening in diaphragm? You are having a diaphragm and you are moving the diaphragm. What is happening in the linear compressor? You are having still the piston and just you are changing the thing. You are now moving that piston using some kind of motor and springs. In liquid compressor, you are still pushing the piston with help of a liquid. What is the common thing in between all these four?
It compresses some constant set amount of volume.
So you are no, because the compressor you will compress. In the cryo also, in other compressor also you are compressing. But what is the different? What is the common thing in all these four and different from others, from other types?
It takes the some amount of volume and then compress it. again it take some amount and again compress it, not continuous process.
Okay, you can say, but still not fully correct. Like what is happening in the electrochemical compressor?
I think compression in one direction is the key. In reciprocating or even diaphragm
So
and all, it
basically
is compressed.
you are giving the you are using the positive displacement. Now you are pushing. You are
Yes.
having a volume and you are using the displacement method to reduce that volume to have the compression. Okay. So in the centrifugal, you are having a centrifugal force and all thing. Electrochemical, you are having the transfer of ions from the membrane. In metal hydride, you are having the chemical reaction. In cryo, you are having liquid hydrogen, then you are pumping it and then you are evaporating it and storing at high pressure. In adsorption, you are having material and absorbing the hydrogen into that. But in all these four, reciprocating, diaphragm, linear, liquid, you are having a particular volume. You are using a piston or a diaphragm or a particular means to compress to use the displacement to reduce the volume. You are using the force, either you are directly connected through the piston or using diaphragm through oil. You are using some kind of force to reduce this volume, giving the displacement, and now you are reducing the volume, then you are having the compression. Okay, so this is the common thing in all these four, but the only thing you are changing the how this should happen. The mechanism of happening of this displacement is different in each one, but finally you are compressing with the help of positive displacement only. Okay, that's why they are known as they are mechanical and positive displacement type compressor. Is it clear?
Yes, yes.
Okay. So very minute detail, but it's good to know it. The answer is positive displacement type compressor. What is the characteristics of an ionic liquid used in ionic liquid compressor?
It is a low melting point salts at room temperature in molten state.
Yes. So for the ionic liquid compressors, we use the liquid ionic liquid that should have low melting point salts at room temperature in molten state. Energy required in kilowatt hour per kg to compress 1 kg of hydrogen using an ionic compressor is 5, 2.7, 10, 5.5.
2.7.
Yes, and it is the lowest among other compressor. The correct answer is 2.7. What is the major difference between an electrochemical compressor and PEM fuel cell?
No gas flow on cathode side in electrochemical compressor.
So let's go through the options. Option D is no gas flow on the anode side in electrochemical compressors. No, because we need to supply the hydrogen on the anode side.
It is
No gas
gas
flow
flow
on,
from the cathode side in the electrochemical
yes,
compressor.
yeah. So the correct answer will be A, but let's see other options also. No gas flow on the cathode side in the PEM fuel cell. Wrong, because we have flow of oxygen. gas flow on the cathode side in the electrochemical compressor? No, because we don't have gas flow in the cathode side. Okay. So the no gas flow on the cathode side in the electrochemical, it is the right answer, because we should have no gas flow. Otherwise, there will be no compression. What is the range of interaction energy involved in adsorption based compressor? So we have not gone through these compressor. So the answer is 0.01 to 0.1 electrovolt. Now let's see something about adsorption based compressor. So no moving part. Compressor is driven by temperature swing. So here we have two process, adsorption and desorption. Requirement is porosity and high surface area of material, because we need to have a material. So because we are using the adsorption, so the porosity should be high and surface area should be also high, so that we can have more and more hydrogen adsorbed on that particular material, and we can have desorption to have the high pressure hydrogen. Possible materials, carbonaceous material, zeolites, etc. It's a reversible process. Adsorption energy is low. Adsorption is an exothermic process, so low temperature required. So this is Nu 100 at 77 Kelvin, 9.9 weight%. 6143 is the surface area. So carbon materials are attractive as low cost, high surface area, and poor volume. They are stable, low weight, like activated carbon have this much of surface area. The thermal management is major requirement for the adsorption based compressors. Advantage, like thermal driven compressor, no moving part, no vibration, noise, sealing not required. Volumetric efficiency is higher, low cost material, high pressure with less number of stages. Disadvantage, thermal management, low energy efficiency, and low temperature operation. So it's emerging technology. So there's a demonstration of input pressure 0.1 to 0.8 megapascal, output 10 to 35 megapascal with flow rate of 3 to 560 meter cube per hour. What is the volumetric energy density that could be achieved for hydrogen compressed at 70 megapascal in a compressed hydrogen tank?
It's a 38 kg per meter cube.
So yes, it's also like it's good if you remember this, because it's difficult to calculate using real gas equations if you don't have all the data. So the answer is 38. The compressed hydrogen tank made up of thin metallic liner and fully wrapped with fiber reinforced composite are called type tank.
Type 3.
Yes. So the fiber reinforced type 3. What about type 4?
It's the polymer inside and outside fiber reinforcement composite.
Yeah. Okay, so these are the questions for today's class. We have covered almost every topic from the previous week. And if you have any doubt, you can email me. Okay. Please do not email the recent assignment questions or any doubt related to the recent assignment questions. Once you submit your assignment, then you can ask me the doubt. Okay, so anybody have any query? Because we still have 5 minutes left. So we can go through.
Can you explain this volumetric efficiency?
Yeah. So volumetric efficiency, you can like you can consider with the density actually, no? So you have a fixed volume. Okay. Suppose your vessel is having a volume. This volume is X, and you are storing gas in this, and suppose that gas is having volume of Y. Okay. So now if your X is fixed, if you increase the amount of Y, okay, so basically what will happen? How can you increase the Y?
Means more compression, increase more pressure.
Yes, you need to, because the volume is fixed and we are dealing with volume. So this volume is fixed, but now you have more Y inside this X volume. Okay, so you need to compress it further and further. So the volumetric density is related to these factors. How much more of Y you can have in a fixed X. Like similarly, the gravimetric density, that is the mass basis. Okay, it is the volume basis.
Okay, okay.
Okay, any other doubt? So all of you are regularly attending these classes, or anybody is having this class as a first or second class?
Amit, I'm able to attend only this class, not the Tuesday's class.
Okay, okay. So I think you missed one class, na? Last class you have missed.
No, I attended. Last Sunday also I attended.
Okay, okay.
And before that, one Friday I missed. Before that, I think no. I haven't missed your class. This is not.
For my case, it sometimes happens at the same time with another class.
Okay.
Sensor technology.
And I think one of you was asking about reference books. Have you found any or not?
At least I have not found.
Okay. Have you gone through this course web page, because they have mentioned the names of reference book on the web page itself?
Yes, but I have not been able to locate some things I need to do.
Okay, okay. So, okay, guys, if you don't have any queries, then we can end today's class. Okay, okay. Thank you for joining.
Thank you.
Okay,
Thank you, everyone. Thank you. Bye bye.